First part of problem 2.20 is to normalize this wave function to find a. We've done this many times before, and this should be trivial at this point. So we know that magnitude of psi of x comma 0 squared being a probability density, if we take the integral from negative infinity to positive infinity of this function, it has to equal 1 because the max probability is 100%. So if you add up all the individual probabilities, you should get just 1 or 100%. If we write this out fully, we have magnitude a squared times the integral from negative infinity to positive infinity of e and the negative a magnitude x squared, so that just carries over into the exponent as a product, so negative 2a magnitude x dx. Note here that this is an absolute value sign, so the integrand stays sort of exactly the same going from negative infinity to 0 as from 0 to infinity, so there's nothing stopping us from just adding on a factor of 2 at the front and rewriting this as 0 to infinity e to the negative 2a just positive x dx. From here, we just integrate this, so 2 magnitude a squared multiplied by, let's see, negative 1 over 2a times e to the negative 2ax from 0 to infinity is equal to 1. And if we write this out fully, then we have, let's see, negative 1 over a times magnitude a squared times, and then this e to the negative infinity is just 1 over e to the infinity, which is 0, subtracted by e to the negative 0, or e to the 0, which is just 1. So the two negatives cancel out, and we have magnitude a squared is equal to a, or a is just equal to square root of little a. And that is part A. Okay, part B, we want to find phi of k, and we sort of already know the sort of Fourier transform formula for this. So phi of k, whoops, this is in blue, I want it in black. Phi of k can be expressed as 1 over square root of 2 pi times the integral from negative infinity to infinity of psi of x comma 0 multiplied by e to the negative ikx dx. So this is just our standard Fourier transform equation. We just plug this in, and this is going to give us square root of a over 2 pi times the integral from negative infinity to infinity of e to the negative a magnitude x, e to the negative ikx dx. From here, we can sort of split this integral into positive and negative x integrals because we have this absolute value sign that we have to get rid of here. So this can be written as a over 2 pi, and then we're multiplying by two integrals. First off, the integral from negative infinity to 0. So x here is always negative. However, because of the fact that we have an absolute value of x, the always negative x's are always going to be positive x's. So e to the ax instead of e to the negative ax to account for that fact, because here, if we get rid of the absolute value, then x is always going to be negative, and that negative sign is going to sort of be retained, and then we have e to the negative ikx staying the same. And then we have an integral from 0 to infinity. This time we don't change anything, we just get rid of the absolute value signs, e to the negative ax, e to the negative ikx. And now we just combine them and we do the integral. So this is going to give us the square root of a over 2 pi times the integral from negative infinity to 0 of e to the x times a minus ik dx plus the integral from 0 to infinity of e to the negative x of a plus ik. Actually doing this integral is going to give us square root of a over 2 pi at the front as always. And then we have 1 over a minus ik times e to the x a minus ik going from negative infinity to 0. And let's close this off with parentheses, and then we have added with negative 1 over a plus ik times e to the negative x a plus ik going from 0 to infinity. And in fact, let's just factor out this minus sign at the front just so we can avoid a bit of confusion with signage. And then we close this off, and now we just have to evaluate everything. So there's a bit of a problem here. Hopefully you see that instantly, in that there's going to be an infinity of an imaginary number. So let's try to sort of resolve what this actually means. But first off, let's write this out fully. So this is going to give us a over 2 pi, and then we have 1 over a minus ik, and then multiplied by e to the 0 is just 1, minus e to the negative infinity times a minus ik. And then we're going to do the same thing here. We're going to subtract by 1 over a plus ik, and then we have e to the negative infinity of a plus ik, subtracted by e to the 0, which is just 1, and then we close this off. So these e to the negative infinity of imaginary numbers are a bit of a problem. So let's try to sort of understand what exactly this means. It turns out that they do equal 0, but let's try to understand why they equal 0. So e to the, and let's, here I actually will write this in blue, sort of just to emphasize that I'm not doing the problem right now. I'm sort of clarifying something. So e to the negative infinity of a minus ik, if we distribute this, this is going to be equal to e to the negative a times infinity plus ik infinity. So we can write the rule of exponents, e to the negative a infinity times e to the ik infinity, because remember, when you multiply exponents, there's exponential values actually add together. Immediately, this is a constant, this just equals infinity, so we're left with infinity times e to the ik infinity. And remember, e to the ikx corresponds to cosine kx plus I sine kx. I left out the x here. So e to the ikx is really just a sinusoid of some kind. So what happens is that if you have sorry, my apologies. This is not infinity. This is 0, because it's 1 over e to the infinity. So that's just 1 over infinity, which is 0. So this is equal to 0 times e to the ik infinity. So e to the ikx is just this sort of trigonometric sum. So, and because of the fact that cosine and sine both just sort of modulate, or they like go within this range, at infinity, there's just going to be some finite value. Cosine of k times infinity is going to be some finite value that ranges between the amplitudes of +1 and -1. Same thing with sine kx. It goes from positive, it goes from positive I to negative I. And either way, these are both finite values, and they're both being multiplied by this term of 0 at the front. So automatically, this term and this term both equal 0. So because of that, we just plug that in, and what we have left is phi of k is equal to square root of a over 2 pi multiplied by 1 over a minus ik times 1, which is just 1 over a minus ik, and then subtracted by 1 over a plus ik times -1. So the two negatives are going to cancel out, and we have plus 1 over a plus ik. And from here, we just sort of combine these two fractions. Remember, look at this, they're complex conjugates, so the imaginaries are all going to cancel out. Everything's going to be neat and tidy. And what we have left is a minus ik, a plus ik, a plus ik plus a minus ik. The two ik's cancel out. What we have left is square root of a over 2 pi times, and at the bottom we have a squared plus aik minus aik, which cancel out, and then minus ik times positive ik. So the two i's make a negative, cancels out with the positive, and we have left is plus k squared over 2a. And that is just our answer. We can sort of simplify this a little bit if we want, and sort of cancel out the 2 at the top with the square root of 2 at the bottom. This is going to give us square root of 2a over pi times a over a squared plus k squared. But that's really as far as we really need to go with this. So that's part B. Part C is probably the most trivial part of this problem, because we're just asked to construct psi of x comma t in the form of an integral, which literally means plugging everything just into the general formula for the Fourier transform, which states that psi of x comma t is equal to 1 over 2 pi times the integral from negative infinity of phi of k times e to the I times kx minus h bar k squared over 2m times t closed off with dk. So this part C is literally just plugging in phi of k. So if we do that, what we have is 1 over 2 pi times square root of 2a over pi multiplied by the integral from negative infinity to infinity of a over a squared plus k squared multiplied by e to the I kx minus h bar k squared over 2m times t. if we want, we can simplify this out a little bit. Sort of the square root of 2 at the top and the 2 at the bottom can cancel out to make a square root of 2 at the bottom. So in reality, this is going to equal, like, 1 over pi times square root of a over 2 pi, and then multiplied by this integral at the front. Copy paste that like this. And this is just our answer, so we're done with C. Okay, final part. We want to discuss the limiting cases where a is either very large or very small. So this is just a question of taking psi of x of t and seeing what happens when a goes to infinity and what happens when a goes to 0, respectively. So the limit as a goes to infinity of psi of x comma t, in this case, if we look at this, we have an a to the power of 3 halves because of the square root of a and a at the top, and we have a squared at the bottom. So the bottom has a bigger power, so automatically this entire thing just goes to 0. So we have a 0 multiplied by a complex exponential, everything just goes to 0. The limit of psi as a goes to 0, or as a goes to infinity, is just 0. We can analyze the limit as a goes to 0 as well. And what we see here is that we have a 0 at the front, so automatically we have a 0 right here. This is going to turn into 0. We also have a 0 from the a over here. The bottom is going to go to just k squared. So automatically this is also going to equal 0. So in both cases, the sort of behavior of psi of x comma t approaches 0 as a goes to either extreme. Now, this seems sort of a little bit weird at first glance, in that, like, psi has to remain sort of normalized, so how could it ever approach 0? However, it is possible for a wave function to generally approach 0 while still sort of remaining normalized, because remember, the wave function can just sort of flatten out and become sort of very spread out and have over a very large range of values, and that sort of does technically allow the wave function to go to 0. And to sort of show what this means, we can look at psi of x comma 0, because unfortunately this equation for psi of x comma t is a little bit too complicated to actually graph. However, psi of x comma 0 is very easy to graph, and in fact we can graph it very easily by just going onto like Desmos and plugging this in for some arbitrary value of a. Say, for example, just for a equals 1, and we can get something, we can get a graph of this. Now what you can do is you can just set it as square root of a e to the negative a magnitude of x, and Desmos has a function which lets you sort of switch the value of a, or like change the value of a on like a scale. And what will happen is that for very large a, where as a goes to infinity, sort of the graph of psi of x sort of approaches something that looks very similar to like a Dirac delta, where psi of x sort of starts going to 0 everywhere except for at this very center point, where it sort of gradually approaches infinity, and that's exactly the definition of a Dirac delta. And technically that sort of doesn't really break any rules, because a Dirac delta isn't really a function. It's technically discontinuous because of the fact that it jumps instantaneously from 0 to infinity at the center point, at the origin, so it's not technically a function. And because of that, it sort of still technically satisfies this condition of like psi of x sort of being 0 everywhere, because it technically is 0 everywhere. The only exception is this discontinuous point at sort of the origin, and that doesn't really sort of break the rule because of the fact that it's just a single discontinuity. Next off, if we analyze the case where a goes to 0, what you see here is that the function gradually starts sort of spreading out and becoming very wide, basically. So eventually, sort of this graph gets more and more sort of short and like fat, and eventually, at the very extreme case, you just have like a straight line that's like infinitely close to the x-axis, and it just spreads out for all of infinity. So this is the more traditional way of satisfying this requirement that psi of x comma t goes to 0, in that it is allowed to approach 0, it just has to get fatter so that it satisfies the normalization condition as well.